Hey, my name is Rick Crosslin, and thanks for inviting me in here to Bridgeport Elementary's 5th grade to teach you what I know about gravity. So gravity is one of the 4 known forces of the universe. So if it's one of the 4 forces, all you got to do is learn 4 of them and you know all the forces that we know. Now 2 of the forces we're not going to talk about today. That's the weak and the strong nuclear force that's around atoms. So we're not going to talk about those 2, but we are going to talk about the other 2. Gravity is the one we're going to talk about mostly. The other force is electromagnetic forces, or electricity and magnets. But today we're going to talk about gravity. Now gravity is actually an invisible force. You can't see it, but you can see its effect. Now, I'm pretty good at this. You guys probably won't be able to do this, but I can do it. Watch. Ready? When I count to 3, I can use gravity, and this will fall. 1, 2, 3. Wow. Amazing, right? You guys are not impressed. Oh, you think you can do it? Come here. Quick. So you think you can do it, ready? Okay. Count to 3 and say drop. So you can't do it. Only teachers can only do this. Ready? Watch. Invisible force. Hold your hand out. I'll show you. 1, 2, 3. Gravity. See how I did it? You're not impressed? You try it. Ready? Say it. She can't do it. Actually, she can. All right. Say 1, 2, 3. Gravity. Gravity. Thank you. But you know what's, thank you. Here's what's cool about this. So here's the Earth, right? This is the Earth. And what I just did, I had that marker right here. See the marker I had right here? And I dropped that marker, and where did it go? It went down towards the center of the Earth. Which means if I was on the other side of the Earth and I dropped it, where would it have gone? To the center. Gravity is a pull force. It's a pull force. Got that? Pull force. Now, this is the part that's probably going to explode your brain. Are you ready? When I drop this, you understand that the marker was pulled to the earth, yes?
Yes.
But what you may not know is that this marker tried to pull the earth up to it. Yeah. I want you to think about that. When I let go of this, it's being pulled down to the earth. Okay, let's take a look. Everybody hold your pencil, and you can turn that and show everybody. Ready? On the count of 3, drop. 1, 2, 3, drop. The earth, do it again. 1, 2, 3, drop. The earth pulled down on your pencil, but your pencil, 1, 2, 3, drop. Also, your pencil pulled up on the earth. One more time. 1, 2, 3, drop. Now that's the weird part about gravity. But the pencil tried to pull, the marker tried to pull the earth up. Which one won? The earth. So why did the earth win? Why did the earth win? It has more, here's the word, mass. Have you heard that word before? Mass. The pencil or the marker has little mass. So gravity is the pull force between 2 objects. The bigger the mass, the bigger the pull. You got that? Now say it with me. The bigger the mass, the bigger the pull. Aha. So what if we have another object like the moon right here, the moon? Now, the moon and the earth are not the same size. Are they the same mass? No. This is 1/6 the size of the earth. So which one has more pull? The earth is pulling it, but guess what? The moon is also pulling, but not as much. Mass is important. So when you think of gravity, there's 2 things you have to think of. First is mass. How much mass something has. And second is distance. How far it is. Let me ask you this. You're standing on the earth right now. I need another volunteer. Thanks for volunteering. It takes courage to volunteer. Get over here. So, what planet are you on? Earth. Turn around the camera. On the count of 3, jump up as high as you can. 1, 2, 3. He came back. Why did he come back? Jump to the moon. 1, 2, 3. Why did he come back? Why?
Because the gravity of the Earth is pulling Michael back down.
That's true. Now, Michael, you jumped up, and if you were on the moon, look here. Here you jumped about 2 feet in the air. On the moon, if you're on the moon and you did that, this would be cool. Jump on the moon. Go ahead, jump. He'd go about 12 feet in the air. But would he come down on the moon?
No. He would.
Yeah.
He would.
He would.
But it would take a while.
It would take less time than on the earth. So on the earth, he's kind of like. On the moon, he's more like. That's an exaggeration. Wouldn't you like to be on the moon playing basketball? But the trouble is, a guy like me could also jump. Have a seat. Thank you. So, the amount of mass affects the gravity. This is kind of weird, Michael. What if you jumped towards the moon? Would there be any time when you got close to the moon where you would be pulled to the moon?
No. Yes.
Let's take a look at that. So before we talk about gravity and mass and distance, let's go revisit mass. So this is, what do you think this is?
The sun.
The sun. So I got this. This is exactly 6 feet in diameter. Now, most of the things when we see the solar system, we don't think about this. But the sun makes up 99.9% of all the mass in the solar system. You want to know why? Because it's big. Check this out. See this right here? Can you see that?
Yes.
That is the size of the earth if it was on the sun.
What? Looks like a little pebble.
It looks like a little pebble, right? This is the size of the earth compared to the sun. This is a 6 foot diameter. You can do the math. 6 foot diameter model. That's a 1/2 inch marble. This would be another planet.
Saturn.
No, bigger.
Jupiter.
Jupiter, a gas giant. If you take a look at Jupiter right here, see that spot I drew on there? That's the size of the storm on Jupiter. The Earth would fit into it. So if we look at these 3 things in our solar system, which one has more mass? Earth, Jupiter, or the sun?
The sun.
The sun. In fact, if you were trying to stand on Earth, not a problem. If you try to stand on Jupiter, you have a couple problems. Number one, it's a gas giant. But let's say you could stand on the surface of Jupiter. It is so much more mass, so much more gravity, that it would squeeze you down and your legs would break and you would be a puddle.
What?
It's like you couldn't stand up. Now, if you could stand on the sun, which you can't, you would be completely squeezed down, smaller than a piece of paper in like 1 second, because it's so big. So size in gravity does matter. So which one's the biggest thing?
The sun.
So what do you think holds all the planets in orbit?
The sun.
And the sun's what?
Mass.
Mass related to its gravity. For example, let me give you this example right here. Here is a model. I'm going to be the sun. This will be a planet. And it is orbiting, right? This is a revolution. 1 year, 2 year, 3 year. But look at the path that it's going in. This is kind of weird. See this path? It's in a circle. That doesn't seem like a natural motion. There was a guy named Isaac Newton. You've heard of Isaac Newton? You know,
Yes.
the guy that
Yeah, drop an apple.
the apple, he noticed an apple fell and he thought, why does the apple fall towards the earth? Why doesn't it just stay? Why doesn't it move sideways? Perhaps there's an invisible force that pulls it down. Right? Sir Isaac Newton, now we know him. And what is that force? Gravity. So he studied gravity and he studied how things move. Now, you look like a nice kid, so stand up. I'm going to stand up right there. I'm going to throw this at your face. That's okay. We got more kids. If you get hurt, we got more kids. No, you just have to let it hit your face. See, Isaac Newton said if you throw an object, it's going to go in a straight line, and it will continue in a straight line unless a force acts upon it. Okay? So when I throw this at her face, it should go straight at her face. We're doing this for science. Okay, ready? Hard, right at her face. Watch what happens. Isaac Newton is going to action reaction. She's probably going to go after the nurse. But also, ready? 1, 2, 3. Whoa, whoa! Why didn't it hit her face? No, I threw it straight. Do you have some kind of invisible force field? Watch, watch, watch. Here we go again. Ready? Right at her face. 1, 2. Watch the path. It's going to go straight. Isaac Newton said it would go straight. 1, 2, 3. Why did it go straight? What?
Because you didn't give it enough force to make it go at her face.
But Isaac said that an object will travel in a straight line unless a force acts upon it. What force acted upon it?
The gravity?
Why did it go down? The gravity made it go down, right? Watch. When I throw it this way, I'm pushing it this way, but gravity's pulling it down. And so the path is, ready? Curved. Hey, throw it to me and see if it works your way. Do it to her. Right in my face. Ah, thank you, gravity. Now, how can I make it hit her face? More force. Let's just see it. Ready? 1, 2, 3. And boom. Yes. Thank you. All right, so have a seat. So what we know about Isaac Newton, he says things travel in a straight line. And what we know about gravity that attracts a pull force, that's how we get this motion.
So the force and gravity is
We'll say it again.
the force of the gravity?
The force of the gravity. So in this model, who am I?
The sun.
The sun. And the green thing is a,
Planet.
and what does the string represent?
Force.
The force of gravity. And if you get closer to the sun, watch what happens. What do you see?
Faster.
And if you're farther,
It goes slower.
it seems that it's farther to go. Now, here's my question. In space, is there gravity?
No.
Really? If there was no gravity in space,
You fall down.
look at this planet. It wouldn't do this. It would do this. Throw that back. If there was no gravity in space, objects would not go in a circle. Objects would follow Isaac Newton's laws of motion, but there is gravity. But you're probably saying, how come then we see astronauts floating around in space, right? Well, I don't know if you can see this. Let me show you right here. Check this out. Here is a picture of the Earth or the Moon. And when you see a rocket going around and around, it's actually not free floating. It's actually traveling at thousands of miles an hour. So if you see an astronaut floating inside of a spaceship, or if you see an astronaut floating outside, it looks like there's no gravity, like they're just floating. But they're actually traveling at thousands of miles an hour. And eventually, you know what the Earth is going to do? Pull them back, and they will come back to the Earth. They will always pull back. But you know what? I can make you famous. Come here, I want to make you famous. Here we go. Here's how we make you famous. All ready? Now, we take you, stand up here. We take this guy, we take you to the tallest building in Indianapolis. We get our camera, we YouTube you. What's your name? Israel. This is Israel. He's going to show you, he's going to be the first kid to show there's no gravity. I'll put you in there, we'll film you. I will cut the cables from the elevator. This will be good. For 5 seconds, look at it. For 5 seconds, he's going to be falling. Look, no gravity. Look, Mom. What's going to happen at 6 seconds? At 6 seconds, gravity's going to come rushing back, and you'll be dead. But you'll be famous. You want to try it? No. Let's try another experiment. Here, Israel, I'll make you famous for something else. Come here.
Oh, God. Is he about to break the wall?
All right. Can we see the floor on this also?
Yes.
Come over here, buddy. Hold that. On the count of 3, hold them like this. Get them right together. They should both keep them even. On the count of 3, we're going to drop them, and gravity should pull them down. But remember, the hammers are also trying to pull up on the Earth, which has more mass? Earth. And so they should go down, right? 1, 2, 3, drop. You're a little slow on the drop. Try it again. Ready? Gravity, an invisible pull force. 1, 2, 3, drop. But let's try this. Ready? Hold this with one hand. Drop, put your pencil down. Hold this. Hold it by the top. Now, boys and girls, two objects, different mass, but gravity is pulling them. Which ones should hit the ground first?
The feather.
Hammer.
The hammer. The feather.
Why do you say the feather?
Come on.
It has less mass. Why do you say the hammer? Because it has more mass. Let's put them even. Put them even at the bottom. Spread them out a little bit. I say they will both hit the ground at the same time. Because the effect of gravity is on both of them. Ready? 1, 2, 3, drop. You see that? They both hit the ground at the same time. Let's do it again. Ready? Watch. Now, air might slow this one down a little bit. And actually, you can look a video up on one of the NASA moonwalks. The Falcon, they took a hammer, a falcon feather, and they did this on the moon where there's no air, and they both hit at the same time. Ready? 1, 2, 3, drop. That's pretty cool. Let's take a look at something else. Okay, now we just lost the moon. You all right? So this next thing I'm going to show you has to do with gravity on a different scale. So here we have the Earth, all right? And here we have the moon. Hold it up like that. So hold that up like that. Let's get these closer together. So look, the size is correct. The moon is about 1/6 the size of the Earth. But here's what I want to know. How far is the moon from the Earth? You think it's that close?
No.
How about there?
No.
What do you think? Tell me when to stop. What about there? Is that, back up a little bit. Hold it up. Back that way. How about that? Look how far, is that how far the moon is from the Earth?
No.
More?
Yes.
Back up.
Thousands of miles.
Well, yeah, but look at the scale. This is thousands of miles to circumference. How's that distance?
Because that is only about like either 2 or a couple of inches. But if you actually went into space,
Yeah.
you would see that it would be.
Yeah, but look,
thousands of
it takes hours to get around the Earth. Let me show you how far it is. Here, let's take this string. Here you go, hold that string. The moon is 9.5 circumferences. Keep going. 9.5 circumferences. Keep going. Help me out here. Keep going. Keep going. Keep going. Keep going and hold it up and keep going and keep going and hold that. Hold the moon up. Put it at the end of the string. Hold it up. Pull a little bit tighter. This is the actual, come on this side so we can see your pretty face. There we go. This is the actual distance. If the moon was that size and the Earth is this size, this is the moon that revolves around the Earth every 29 days and some hours. That is kind of far, isn't it?
Yeah.
Now, who's pulling who? The Earth is bigger, so the Earth keeps the moon from going into outer space. But the moon also pulls on the Earth. And that's how we get our tides. Now I got to show you something. Check this out. 50 years ago, we had a rocket that took off from the Earth, but it couldn't get to the moon. Here's the problem with rockets. If you fill them this full with fuel and take off from the Earth, they try to go up, but what will pull them back? Gravity. So we need a bigger fuel tank. So if they put another fuel tank on here, now we have double the fuel tank, but now this is all empty, and even when the fuel's gone, it's too heavy. Let's put another one on there. So now we have 3 stages. Here's how they solve the problem. A giant rocket called the Saturn V takes off. And after less than a couple of minutes, this fuel is all used up, and this goes back to the Earth. It burns up, and now this is going faster and faster, and it's burning up this fuel. You know what happens next?
That one falls off.
The second stage falls off. Now this is going faster. It's using the Earth's gravity, and finally, they head towards the moon. This one burns up. Hold that. And now we're going thousands of miles an hour towards the moon. If we stopped right here, what would happen? You wouldn't fall because there's...
You stay there forever.
No, what would pull you back? It might take a year that it would pull you back and they'd all be dead. 3 men. But they're going fast and fast and fast. Here, if they stopped right here, where would they be pulled back to? The earth. No, look, they're still, remember it's big and they're close to it? Back to earth. If they got here halfway, if they stopped halfway, which way would they be pulled? Because it's bigger, right? In fact, they will keep going until they get right about here. And guess what this is called? Translunar injection. So right about here, the earth stops pulling, and what starts pulling?
The moon.
The moon. And as they go, it'll pull faster and faster and faster until
They're on the moon.
they were on the moon. Now when they got there, they went around the moon. 2 guys got in a small part of the capsule, landed on the moon. Michael Collins by himself orbited the moon. While they walked on the moon, it's time to come back. They fired the last of their fuel. And we just destroyed them. Hold that. Pull it tight. For 3 more days, 3 days there, a day, 3 days coming back, they're coasting. Now they're getting closer. They have a problem. If they hit the earth, they're dead. If they miss the earth, they're dead. If they come in too shallow, they're going to bounce off the atmosphere and they're dead. If they come in too steep, rub your hands together. Feel that heat?
Yeah.
If they come in too steep, they'll burn up. They're dead. So they have to come right at the right angle, slow down. They catch fire on purpose. It's called ablative materials. The parachutes come out and they land. So that's pretty cool. The gravity of the moon and the gravity of the earth and the rocket fuel to take over. But I'll tell you, guys want to hear something really amazing? Yes? That was Apollo 11. Apollo 12 went up. Everybody thought it was cool. Apollo 13 starts. People were bored. Nobody wanted to watch it. A few people did, but we had a war going on. We had people fighting each other in the streets over discrimination. And everybody lost interest in going to the moon. And now that was Apollo 13. Now here's what happened to Apollo 13. This is kind of cool. Hold this. Ready? So Apollo 13 takes off. And after about the first day, they're right about here. And something really weird happens. Ready? Here's what happened. They were supposed to turn a switch that was supposed to mix some oxygen. Now they didn't know this, but when they turned that switch, it sparked a fire and it blew out the whole side of their spaceship. They're going thousands of miles an hour towards the moon. They're right about here. Their spaceship is out of control. They have less than 30 minutes. They're going to be either dead or out of air. They have to figure out what to do. They can't stop. If they turn the rocket around and fire their rockets to slow them down, they'd get right about here, and it would take them years to get back to Earth. They'd be dead. If they didn't do anything, they'd be out of oxygen. They'd be dead. The moon, the thrust is still pulling on them. The Earth is still pulling on them. They figured out in real quick time to fix their air, to stop their rotation, and to keep going. They all climbed in the front part of the command ship, turned all the electricity off. If they could get to the moon, how are they going to get back? And when they come back, if they turn on their spaceship turn back on. This was an amazing thing that they had to solve. Here's how they solved it. This is pretty cool. So they're going to the moon. They fix the air. They're headed to the moon. I need another volunteer, somebody that's kind of strong. It doesn't mean to be pulling around a little bit. Let's see. Thanks for volunteering again, Michael. All right, Michael is going to be Apollo 13, okay? All right, Michael, you just take it off, and right here, you're destroyed. Sorry. Screw her a little bit, my friend. All right, Michael is going to be, hold that like that. Michael, you're going to be coming towards me. And when you come towards me, here comes Apollo 13. And if he misses the moon, he's dead. Do it again. If he comes, I'm in the moon. Keep it, come at me. If he hits me, he's dead. Go back. Let's try it again. Here's what I need Michael to do. Go back, Michael. Oh, we got another alien coming in.
Alien.
Put your arm right here like this. Put that arm. You go fly. Go past me fast. I'm the moon. All I can do is pull him. Keep that arm high, tight. Go. Now do it again, faster this time. Watch what happens. Here comes Apollo 13 on the moon. Watch what I'm going to do to him. Grab your arm hard. Keep going. Fast. And when I grab him,
Whoa.
that was weak. Michael, do it again. Michael, hold your arm stiff. Go that way as fast as you can. Go. Go, go, go. Wow. And see how I spun him around like that? That was what Apollo 13 did. But you got to go faster. You do it one more time fast.
Mr. Crosslin?
Wait, go. Fast, fast, fast. And see how? Did you feel the pull?
Yeah.
They used the moon's gravity to slingshot Apollo 13 back, and luckily everything. Thank you, Mike. You have a seat. Everything came back on, and they were able to land. So Apollo 13 was pretty much an engineering and a human miracle that they did all that. So I want to show you guys something that's pretty amazing. I have here the world's strongest magnet. This magnet is really, really strong. So strong I want to be careful about it. We're going to use that as a model for gravity, okay? So this is a strong magnet. It attracts other magnets or iron. I just happen to have some iron balls if they come towards us here.
Whoa.
It's really strong. Now, what I hope to do, let me move back out of here. I have a ramp, and I'm going to let some marbles, these steel marbles or ball bearings, go towards this. And this, if this works right, it's really pretty cool. They're going to come towards you three right there. So just grab them if they come. So here we go. So I'm going to down the ramp, and just just rotate the cart, and you can see the ramp right here. Can you see the ramp? Mm-hmm. Okay. And I'm going to let this go down, and we'll see what happens. Let's go back and focus on the strong magnet. So if I miss, this is what happens. Ready? Too far. Hold that one, please. Grab that one, please. Now, if I get too close, this is what happens.
Oh.
But what will happen, now this is the cool part, what would happen if I get close enough, here's an object going in a straight line, the gravity of this pretend planet pulls it, what do you think the path of this will be? Straight?
No, curvy.
Curvy? Let's find out. Ready? Watch. If I can do this, here we go. Nope, they died. Here we go. Ready? Oh, too close. If I get too close, still too close.
45.
Do you see any curve? Let's try it again. Here we go. Nope, too close. Let's try this side. Ready?
It curved a little bit.
Too far. Here we go. Oh, a little bit of curve. You see the curve? Watch. Here comes a good one. Nope.
Oh, maybe.
Nope.
Just grab it.
Oh, a little bit of a curve. Here we go. Oh, you see it? You see that? See the curve? Now what you're seeing is the gravity pulling that, instead of it going in a straight line,
It curved.
it curves. Let's try it a couple more times here. Ready? You see that curve? Uh-oh. Here we go. Ready? This will be the best one. Nope. Nope.
There's a big green one. Nope.
There was a curve. You see the curve? So this model shows there's a good curve. This model shows what happens if you get too close, that happens. But if you get just right, it curves. All right. One more time. Let's try it. Nice. Ladies, roll those back towards us. See what happens. Go towards the magnet. And pause.
Yeah, go.
Here is one more example, a model I want to show you about gravity. Let's say this is the universe, and here is an object. This object in the universe doesn't seem to have any movement at all. There's no force acting upon it. But what would happen if we added a star? And that's where I have this massive, this is a cannonball. It weighs quite a bit. As soon as I put it in here, this is going to be our model of a star. And now, no, this is not a trampoline. This is a model of the universe. That is a star. Here is a planet. Now, you'll notice how I do this gently. And watch what happens to the path of this planet.
It goes in a circle.
It goes in an orbit, and it's elliptical. It's not. Look, it goes faster when it gets closer to it.
Like gravity?
Because it's slightly smaller.
Why can't I shut the museum?
The hole is getting smaller.
So what I'm trying to, it's getting smaller and went faster. What I'm trying to show you is this is what a star does to a planet. But most stars in the solar system are binary. You know what binary means?
No.
Two. So most stars are double. Now that means twice the mass. Let's not lift it up, right? Twice the mass. If it's twice the mass, it's also twice the,
Pressure. Force.
what's the word on the board? Say it.
Gravity.
What's our lesson about?
Mass.
Gravity.
So I'll say it again. If it's twice the mass, it must be twice the
Gravity.
gravity. So you got one of these guys and two of these guys, twice the gravity. Here we go. See what happens now. Pull that so it's not. There's no wrinkles like that. Here we go. Ready? There we go. Let's see what happens. Ready?
It's going
It's
faster.
going faster, and the more objects, the more planets going around a star, and even the different sizes of them. Now you notice some go faster. What would happen if one's going in the other direction? It will collide sometime, and then they'll all end up going in the right direction. See how that affected the system?
All of them. Drop them all.
So this shows you, and the more planets that join there, what does that do to the mass? Makes it bigger, so it makes the gravity bigger. So,
What if you drop them all in?
well, if I got this one going and that one going, and I got one going that way and the rest going this way, that's going to collide eventually, and eventually they will all go in the same direction. Now, if you notice how I'm doing this, I'm just pushing it gently. In a minute, I'm going to let you do it. If you push it too hard, they will go out of the circle and the model won't work. So gravity has to do with mass and distance.
I'm not listening.
Last one, last one. Very satisfying.
I'll probably say the museum. It's heavier.
All right, so here's what we're gonna do. I will give you one.
With my coin.
I'll give you one, and here you go. Take one, pass them down, and take one, and take one. And you can take two if you want. Take two. Pass them down.
Yeah, Mr. Crosslin.
Everybody take two.
I got one.
Pass them down. Take two. And
He
pass.
said we can take two.
Take two. Pass them.
I got one. Got two.
Take another one. Take another one. Everybody have two?
No. Please. These are heavy.
Everybody?
One more. These are heavy.
Anybody?
I got two. I got three.
All right. So once again, are we ready?
This guy got
Here we go. Quiet, please. So this is our model of a binary star system. Now, if you throw it hard, they will go out and it won't be a good example. So watch it one more time. Keep your hands back. Because if you put your hand there, no, I didn't say lift it up. That's good. Keep your hand back. When you throw it, move your hand back. Ready? Watch me. And there's one. And you guys can join. Go ahead. There's one. Move your hand back after you do
Look
that.
at mine. Mine are going so fast.
Move your hand back. Sideways. Nice. Good throw. Good throw. Oh, here we go. Look at that. Look at that. Oh, collision.
One of those was mine.
They racing. Look, they racing.
They are racing. The ones closer are going fast.
Look at that one. Look at that big one.
The gray one is mine. That one is mine. Virtuals?
Some alien threw it.
Some alien
Nice.
threw
Is
it.
that everybody?
Yeah.
Here we go. All right, so that was our lesson on gravity. Gravity is a visible force, one of the four forces of the universe. It has to do with how massive something is and how far away it is. Thanks, guys.